Hello everyone and welcome to Seminar 6 of your course. Slightly unconventional form of instruction today, but I hope it will be just as helpful. As always, you are welcome to email your questions in and we can find the best way to address any doubts. The topics covered in today's seminar are related to closed loop stability. That is, how stable is the behavior or response of the process when it is being managed by a certain controller. In order to assess the stability of the closed loop, we use the general stability criterion, which in turn uses the characteristic equation. There is also the root stability criterion. This criterion has both necessary and sufficient conditions required to be met by the closed loop for stable behavior. And finally, there is the direct substitution method, in which we specify the desired closed loop behavior. All these topics are, of course, already taught to you by Dr. Lee and available in your eClass lecture notes. But to make it easier for you, I will also recap these concepts as we go through the seminar. So let us move on straight to the questions. In question 1, we are given a process described by the transfer function g of s equals k over tau s plus 1 times s plus 1. Our tasks are as follows. If we choose to control this process using a proportional controller or a p-type controller, what sort of controller design gives stable closed-loop behavior? Next, if we choose instead to control the process using a proportionally integral controller or a PI controller, what sort of controller design gives stable closed-loop behavior? And lastly, by adding integral action via the PI controller versus the P controller, are we stabilizing or destabilizing the system? Let us begin with the solution to part A of the question. Here, we choose to control the process g of s using a p-type controller. This controller is described by the transfer function gCA equals kc, which is the gain of the controller. Therefore, the open loop transfer function becomes the product of the process transfer function and the controller transfer function. This open loop transfer function is represented by GOL and is given by k over tau s plus 1 times s plus 1 times kc. The characteristic equation of the closed loop described by the above controller is given by 1 plus gl equals 0. Here, recall that the characteristic equation relates to closed loop stability in the following manner. The location of the poles of the closed loop transfer function on the real imaginary axis determines the closed loop stability of the system. These poles are calculated as the roots of the characteristic equation. Therefore, if these roots or poles have negative real parts, then the closed loop system is stable. Therefore, we now look at the characteristic equation of the closed loop system in question to describe or to determine what values of system parameters give stable behavior. We can rearrange the characteristic equation in the form of a quadratic equation and note that in order for a quadratic equation to have negative real parts in its roots, the constant term must take a positive value. In this case, the coefficient of s also takes a positive value since tau, the time constant, is positive. Therefore, when we choose a proportional controller for this process, we must ensure that the product of process and controller gains lies between -1 and infinity. Therefore, the final solution for this part is given as follows. For the given process, using a proportional controller, stability is achieved when the product of process and controller gains lies between -1 and infinity. Moving on to part B now. Here we choose to control the process g of s using a proportionally integral controller. This controller is described by the transfer function gcb equals kc times 1 plus 1 over tau I s. As in part A, we find the open loop transfer function denoted by GOL, B. The characteristic equation in this case is now 1 plus GOLB equals 0. As in part A, we can rearrange the characteristic equation in the form of a cubic equation. Since this is a cubic equation, the root stability criterion is employed to assess the stability requirements. The root stability criterion has necessary and sufficient conditions to be fulfilled for stable closed-loop behavior. Let us go over a quick recap of the root stability criterion. For any characteristic equation of order n, represented by the equation in red, the root table or array can be written as follows. Then, for such an equation, the necessary condition for stability is that all an coefficients are positive. The necessary and sufficient condition is that all the coefficients in the in the first column of this root array are also positive. This means that an minus 1, b1, c1, and all the way until z1 must be positive. Note that the calculation of b1, b2, c1, c2, and so on is given on the right-hand side. As you will notice, they are simple cross multiplications of the coefficients of the characteristic equation. Stability criterion with the characteristic equation in green, the necessary condition says that Kc times K must be a positive value. In order to employ the sufficient condition, we draw the root array as shown. The B1 and C1 terms in this case need to be positive quantities. The positive enforcement on C1 is already taken care of by the necessary condition, so we focus on the positive enforcement on B1. Additionally, we note that the numerator term of this B1 must be positive since the denominator contains only tau I and tau terms, which we know to both be positive. Therefore, enforcing the numerator to be positive, we have the following relations. Since tau I and tau are always positive, the RHS is always negative. We now have two cases to consider. Regarding the LHS, in case 1, the LHS term is a positive value. Then we have the relation Kc times K is greater than minus tau I times tau plus 1 over tau I times tau plus 1 minus tau. However, this is a less restrictive condition than the necessary condition itself, which says that Kc times K must be greater than 0. On the other hand, in case 2, the LHS term is taken to be a negative value. Then we have the relation Kc times K is lesser than minus tau I times tau plus 1 over tau I times tau plus 1 minus tau. Coupled with the necessary condition, we have both an upper limit and a lower limit on the product of controller and process gains, and therefore this is the final solution. Regarding the stabilizing effect of adding the integral action, we notice that the stable region for controller settings becomes more limited when we add integral action, regardless of the case whether LHS is positive or negative. Let us now move on to question 2. In this question, we are given an open loop transfer function for a feedback control system. We are asked to design a proportional controller, GC equals KC, using the root stability criterion. Note that in this case, in the open loop transfer function, we have a time delay term denoted by the exponential to the minus 3s, and so we cannot directly implement the root stability criterion here. We first need to approximate the time delay term using Paddy approximation. Therefore, using first order Paddy approximation of the time delay term, we have exponential to the minus 3s equivalent to 1 minus 1.5s over 1 plus 1.5s. Then the characteristic equation is given by 1 plus the open loop transfer function equated to 0. This is further simplified to obtain a quadratic equation in S. It is useful to note that for characteristic equations which are quadratic equations in S, it is easy to solve for the stable controller settings without the use of a Roth table, because the necessary condition acts also as a sufficient condition. Therefore, we just need to ensure that all the coefficients of the characteristic equation are positive values, which in this case means that 11.5 minus 0.75 times Kc is greater than 0, as well as 0.5 times Kc plus 1 is greater than 0. Solving for these conditions, we have the range of Kc values that gives stable global closed loop behavior to be between -2 and 15.33. 3 now. We are given a process, which is the reboiler unit of a steam distillation column. This process can be represented as a transfer function between its output and input, the liquid level in the reboiler and the steam pressure respectively. The control schematic is shown in the figure. Furthermore, we are told that the transmitter and control valves in this process have negligible dynamics, which means no time constants are involved, but have steady-state gains of 0.5 and 2.5 respectively. The task is to design a level controller using the direct synthesis technique. Note that no controller design structure, that is proportional or PI or PID, is explicitly given to us here. Let us have a quick recap of the direct substitution method. In this method, we seek to obtain stability limits of a closed loop by using the concept that if the poles of the characteristic equation are on the imaginary axis itself, which is shown by the green crosses in the figure, then the system is marginally stable. Therefore, we usually just substitute S equals J times omega to obtain the stability limits. And this is easily done for proportional controllers or specifically designed controllers. However, for a more general case, the desired closed loops behavior can simply be specified, and we can equate the actual behavior to the desired behavior to obtain the GC structure. Therefore, let us first obtain the closed loop transfer function of the given control system. The closed loop transfer function between the control variable y and its set point ysp is given as follows. It is given by the product of transfer functions in the forward path, which is gc times gv times gp, controller valve process, over 1 plus the product of all the transfer functions in the control loop, gm times gc times gv times gp, which is transmitter, controller, valve, and process. We now need to choose our desired closed loop behavior in order to obtain the controller structure GC. Let us choose our closed loop behavior to be that of a first order process by keeping the process zeros intact in the numerator. Then, by equating the actual behavior to the desired behavior, we obtain the structure of GC to be minus S times 3S plus 1 over 4 times tau C plus 1 times S plus 2. As you can see, for certain values of tau C, for example 1.25, the GC structure becomes that of a purely derivative controller, which could lead to unstable behavior. Therefore, let us switch our desired closed loop behavior to be that of a second order process, which is given as follows. Then, by equating the actual and desired closed loop behaviors, we obtain the controller transfer function to be minus S times 3S plus 1 over 4 tau C square S squared plus 8 times tau C plus 1 times S plus 2. And this is the final solution for question 3. This marks the end of this seminar. I hope this was clear to you. Please feel free to email me with any questions and we will work out the best way to get all of your doubts sorted. Also, please email with any feedback on how the seminar is being conducted. This will help me make better videos for the rest of this term. So take care, stay healthy, and see you all at the next seminar. Thank you.